Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its artificial intelligence solutions for hydroclimatic resources state estimation. KALMAN filter. These resources are water, sunlight and wind. Part 2. KALMAN filter. Math modeling. The working paper theory of dynamical systems under uncertainty contains the theory related to the KALMAN filter and its variations. What is climate change? Climate change refers to long-term changes in temperatures and weather patterns. Such changes can be natural, due to changes in the sun's activity or large volcanic eruptions. But since the 19th century, human activities have been the main driver of slow climate change, which is accelerating at an exponential rate, mainly due to the burning of fossil fuels such as coal, oil and gas. The burning of fossil fuels generates greenhouse gas emissions that act like a blanket that wraps around the Earth, trapping the sun's heat and raising temperatures. The main greenhouse gases that are causing climate change are carbon dioxide and methane. For example, using gasoline to drive a car, or coal to heat a building. Clearing forests also releases carbon dioxide. Agricultural operations, such as animal droppings, and oil and gas uses are the main sources of methane emissions. Energy, industry, transport, construction, agriculture and land use are among the main sectors causing greenhouse gases. Global warming induced by climate change has resulted in an intensified hydrological cycle. Consequently, there is an increasing occurrence of extreme hydroclimatic events, such as floods, droughts and heat waves, accompanied, in recent decades, by an increase in the extreme, maximum and minimum magnitudes of hydroclimatic variables, in many regions of the world. In addition to this increased volatility, one of the impacts of climate change is that the regulatory capacity of current infrastructure for extreme events decreases significantly. For example, the reduced effective capacity of reservoirs to regulate water resources will lead to increased flooding and increased rationing, which may surprise unsuspecting water resource managers. On the other hand, temporary displacement linked to climate change is not something related to a hypothetical future, it is already a reality. An annual average of 21.5 million people have been displaced each year, since 2008, by sudden climate-related threats, such as floods, storms, wildfires and extreme temperatures. From the point of view of mathematical modeling, this implies that the knowledge developed in the management of natural resources must be reviewed, since the behavior of physical systems is changing, in such a way that we have decreased the ability to predict changes, because we do not know how they are generated. Hopefully, the physical laws of the processes won't change, but the parameters and seasonality change as you travel through time. Then we need new mathematical forecasting models, which adapt to a constant change that did not occur before. The HI methodology involves linking predictive and prescriptive artificial intelligence methods, to give rise to decision-making artificial intelligence. This lecture discusses predictive analytics models. Satellite image data reconciliation. The starting point of the hydroclimatic variable prediction process is the available satellite images, original or pre-processed, for many of the variables involved in the process. This topic is not covered in this presentation, it can be consulted in another video specialized in the subject. Uncertainty dynamic systems. State estimation approach. Predictive analytics models, forecasting. Based on hybrid models, model-driven plus data-driven, supported in state estimation methodologies, more specifically improvements and variations of the KALMAN filter, KF. Overall, the minimum functions of these models are smoothing, filtering and forecasting of the viscosity value of the crude oil transported in real time at any point of the pipeline, taking into account that, on a daily basis, laboratory tests are carried out to establish the viscosity value that is being transported. This actual viscosity data is confirmed a day after the shot by analysts. Smoothing, filtering and forecasting of the viscosity value of products in real time, assuming that an inline viscometer is available. However, the measurement of this is not exact, but it maintains precision, and allows you to verify the trend of the measurement. Identification of the operating periods during which, Due to the quality of the product, density and viscosity, the dosage applied affected the transport of hydrocarbons. Given the characteristics of KF, smoothing, filtering, and forecasting of the value of the pipeline's operating variables at any point, using the pipeline's physical model, and smoothing, filtering and forecasting of the value of pipeline parameters, e.g., roughness, slope, etc., when it is considered that these may be subject to uncertainty. Database algorithms only consider the database of observations, historical or synthetic, to determine the dynamic prognosis of the physical process. Normally, the related professional is a data scientist. Model-based models are based on the numerical simulation model, which must be fitted by means of algebraic expressions, to be expressed as a system of stochastic differential equations, or finite differences, or finite elements. This requires an expert in the field of interest, in this case fluid mechanics, mainly in the transport of petroleum products. This requires an expert in the field of interest, in this case fluid mechanics. The integration of the two approaches gives rise to hybrid predictive analytics, which can be considered as the appropriate method, that takes advantage of the mathematical knowledge of the physical system, and historical information. The most well-known method, and most used, for more than 65 years, is the KALMAN filter. The state estimate describes the system based on state variables, characterized by discrete, empirical probability distributions, and dynamic, empirical, probability distribution functions that evolve over time. On the other hand, the predictions that can be made with the state estimation methods cover the entire horizon of the period under study. Smoothing, predictions about the past. Forecasting, predictions about the future, and filtering, predictions for the present. In a system under uncertainty, correcting the past may be just as important, if not more so, than forecasting the future and estimate the present. In practice, all the variables that exist in spacetime can be measured and subjected to state estimation processes. Examples of applications of the KALMAN filter for hydroclimatic variables are smoothing, filter, and forecasting of water flow, precipitation, radiation, and wind speed. KALMAN was best known for his co-invention and development of the KALMAN filter, a mathematical linear algorithm that since its origins has been widely used in signal processing, control and guidance systems, navigation and control. The approach for the state estimation, SC, is supported on a conception of the stochastic processes, where the random variables are clearly differentiated of the measures, being understood that the modeler has data of the measurement system, that may be different from real values of the random variables. Therefore, all available observations are considered as random variables, having their measure information, but which, by reason of the randomness of the measuring system, are subject of precision errors, therefore, assume them as deterministic induces errors. Moreover, there might be more than one measure for a random variable, obtained by different sources. Two types of noise, or errors, are considered in state estimation modeling. Estimating the state involves a dynamic and cyclical process, in which the following occurs. 1. At time t1, we start from an a posteriori multivariate probability distribution function, PDF, of the state variables. 2. Using the information up to t1, an a priori estimate of the PDF for time t is made. 3. Simultaneously, the observation system produces the multivariate probability distribution function of the measurement variables. 4. By combining the a priori information of the state variables, with the information of the measurement system, a new a posteriori PDF is obtained, for time t. This process results in a reduction of uncertainty, volatility, about state variables. As a general rule, it is considered appropriate to use an extended KALMAN filter, or a dual KALMAN filter, to simultaneously estimate state variables, and the parameters of the equations. State estimation and KALMAN filtering. The interested professional can see detailed information in another complementary video that presents its artificial intelligence solutions for hydroclimatic resources state estimation. Rudolf, Rudy, Emil KALMAN was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. The KF process has as its starting point the dynamic equation of state variables, which has as its input the a posteriori prediction in t-1, and the control variables in t. The result is the a priori estimate of the state variables for period t. Using the observation equation, KF produces the a posteriori estimation of the vector of measures zt. On the other hand, the system that is being observed, through the measurement system, produces the actual measurements. The comparison between the estimate a priori of zt and the real value of zt produces an error, or innovation, that is used to make corrections in the state variables. This is done by means of the so-called gain matrix, M, which is a central part of the KF. The result is the a posterior estimation of xt, which will be the starting point to carry out the process in the next period, t+1. Variations and extensions of Kalman filter. Considering that KF is oriented to linear dynamic systems, an effective algorithm for identifying an industrial, or a natural process, may be considered as a combination of the following methodologies. Kalman filter, extended Kalman filter, ensemble Kalman filter, dual Kalman filter, Bayesian model combination, and multiple Markovian state Kalman filter. Multi-methodologies Kalman filter. The advantages of the approach based on the integration of multiples methodologies of state estimation versus the classical methods are presented below. One of the limitations in the modeling of uncertainty dynamic systems is that related to the hypothesis that the response function is known a priori, and structural changes of the system cannot be easily modeled. The response function of a system reflects the way its internal structure works. Structural changes cause changes in the response function and cannot always be expected. Many of the changes that occur in the behavior of a system are consequences of unexpected events. Before these eventualities, schemes based on multiple system states, or similar, to determine the moments in which structural changes occur, differentiating them from pure stochastic effects. From the point of view of control, the state estimation allows the online analysis of the phenomena that are occurring, while conventional methods are aimed at ex post analysis, to describe phenomena already past. Climate change generates structural changes in natural resource systems, that cause changes in response function, which cannot always be expected, but they can be discovered using deep learning methods, typical of artificial intelligence. Smoothing state estimation. Predicting the past. Smoothing is fundamental in the process of estimating the state of hydroclimatic variables, because due to the type of process, it is necessary to reconstruct, in the best possible way, the history of all the highly correlated variables. For example, if for a special, unknown, or unmodeled reason, an incorrect measurement occurs, it will cause future predictions to fail. The error will remain in the system, inducing new errors, if this measure is not corrected. This position is part of the traditional approach, which assumes that the measure is deterministic and cannot be corrected. In the process of state estimation, all system variables, including measurements, can be corrected by making a posteriori prediction of the past. This will significantly improve predictions of the future a priori. State estimation is a hybrid method of artificial intelligence, as it models the measurement system and mathematically models the physical processes. In Hai's opinion, it is the most robust method out there. Dual state estimation of state variables and model parameters. When the true value of the parameters, of dynamic the equation of state variables, is unknown, it is necessary to use a variation of KF, like EKF, the value of system state variables when the structure and parameters of differential equations are known for certain. Extend Kalman's theory to systems of nonlinear equations. NKF. It is a recursive filter suitable for problems with a large number of variables, such as discretization of partial differential equations in geophysical models. The NKF essentially replaces the covariance matrix by the sample covariance. DKF. It uses two filters that act in parallel, one on state variables, and one on parameters of a statistical model, or of the physical model, and UKF. It belongs to the particle filter, PF, methods that are recursive implementations of Monte Carlo-based statistical signal processing. When the true value of the parameters, of dynamic the equation of state variables, is unknown, DKF uses two filters that act in parallel, one on state variables, and one on parameters of a statistical model, or of the physical model. Based on this approach there are multiple theoretical variations. Here will be considered the one presented by Labar et al. The diagram summarizes the process. The diagram shows the connectivity of the standard Kalman filter. The DKF includes an additional filter on the parameters, in order to simultaneously correct state variables and parameters of the dynamic equations. Multi-Markovian system state Kalman filter. Kalman's filter theory, KF, can be extended to consider systems whose dynamic representation implies that the system, as a whole, can change state randomly, so that it is not known exactly how any of its components respond. In 1978, Velázquez Bermúdez developed the multiple state Kalman filter, MSKF, which corresponds to the extension of Kalman's filter theory, to model systems whose dynamic representation depends on the state, or regime, in which the system is located. There are plenty of examples that can be cited. In all of them the response of the system, person, basin, client, epidemic state, can respond to stimuli in the environment in accordance with the state in which the system is located, which in many cases is not fully identified, because is a random variable. System states can be associated with a semi-Markov process, time-dependent transition matrices, where the probability of transition from one state to another is known, or estimated, for any period of delta t length. In this case, the regime, or the state of the system, should be considered as an additional state variable that should be estimated inline. The system state is associated with a state of a Markov chain. An example of a system states might be: in a client, happy, normal, unhappy. In a pandemic, the epidemic state, stable, growing, deceasing. In a watershed, dry, wet, in transition. MSKF makes it possible to assume dynamic structures for parameter variation, which leads to more flexible models than those obtained using limited tools, offered by classical methods based on statistics. It should also be understood that the state estimation process corresponds to a Bayesian inference process, where estimators are recalculated when new information arrives. From this point of view, the identification of the behavior of a system is not limited to evaluating parameters that summarize the average behavior of the system due to the integration of its variability and a last period, and from there consider the calibrated model as a static model. The combination of information to determine the state of the system is based on Bayes' theorem, which can be written as: the a posteriori probability is equal to the a priori probability, multiplied by the likelihood function of the data, divided by the probability of the data, which is assumed to be equal to a constant that normalizes the sum of the probabilities equal to 1. Therefore, if a process is being observed through n models, potentially valid for the identification of the state of the system, there are n systems of equations, one for each model n, to perform the Bayesian combination of all the information. The real problem is the determination of the estimators of the parameters that represent the best dynamics of the system, according to the observed data for the current instant, the time t. It involves concentrating the effort on the evaluation of the big changes that are taking place. Then it is possible to determine in real time the structural changes of the system, which are reflected in changes in the values of the parameters, which in classical models only happens after these changes have occurred. In the context of climate change, we need to identify these changes in real time. Hydroclimatic state estimation under climatic change. The following are the advantages of the HI's approach to state estimation over classical methods, including standard Kalman filter. One of the limitations in modeling uncertainty dynamic systems is the hypothesis that the response function is known a priori, and that structural changes in the system cannot be modeled. But the system's response function reflects the way its internal structure works. Structural changes cause changes in the response function, and standard models can't always detect them. This is the case of climate change. Many of the changes that occur in the behavior of a system are the result of unexpected events. In the face of these eventualities, multi-state schemes should be used to determine the moments at which structural changes occur, differentiating them from pure stochastic effects. From the point of view of control, multi-state estimation allows for online analysis of phenomena that are occurring, while conventional methods are aimed at ex-post analysis to describe phenomena that have already passed. To explain the use of MSKF, the modeling of the precipitation runoff process in a basin will be taken as an example. This type of model relates the precipitation that falls in the basin to the flow in the river using the instantaneous unit hydrograph function. This process is linked to the hydrological cycle, which, depending on the size of the spacetime, must be included in the model. Normally, the dynamic change of response of large watersheds has been occurring on an annual cycle, which is conventionally modeled based on monthly seasonality. It is more generally associated with the 4 seasons into which the annual cycle is divided, which moves around the Earth dynamically. The graph shows the change in the response function of a watershed in which winter occurs at the beginning of the year and summer in the middle of the year. The change in the unit hydrogram is directly related to the season. In winter, the basin is filled with water, the surface and aquifers, and therefore a drop of water drains immediately, and the time it takes for rain to pass through the basin is minimal. The flow of the river will be the maximum. In summer the situation is different, the basin is dry, the surface and aquifers are empty, and therefore a drop of water goes to these reservoirs, and the time it takes for the rain to pass through the basin is maximum. The flow of the river will be the minimum. From summer onwards the response function begins to change, the reservoirs begin to fill up until summer arrives, when a new cycle will begin. In a large basin, this dynamic of the response function will occur smoothly, over the months. In a small basin, or with very little storage capacity, this transition can occur in hours. With respect to climate change, we can define a steady state of climate change, which is distinguished by the fact that seasonality is non-volatile and well-defined. That is the situation that the last generations have experienced. With respect to climate change, we can define a steady state of climate, which is distinguished by the fact that seasonality is non-volatile and well-defined. That is the situation that the last generations have experienced. Climate change has generated high volatility and seasonality, summer days in winter, and vice versa, and longer, or shorter, seasons. All of this leads to stationary models losing predictive power, as they can't answer the questions of how, when, where, since the whole climate is moving in time. In common words, it's going crazy. Another process we are experiencing is the increase in the volatility of natural phenomena. Now, the valleys are smaller, and maybe more extensive, and the peaks are higher, but maybe shorter. This is related to the water cycle, which now has a greater volume of water circulating, which has changed behavior patterns. MSKF behaves like an artificial intelligence algorithm for deep learning. MSKF can start working with empty information, and as it receives information, it adjusts based on the observed sample, allowing it to be used in almost unknown processes such as climate change and a new pandemic. Use case: forecasting hydroclimatic variables. Case: projection of the ENSO, El Niño, phenomenon. ENSO, El Niño Southern Oscillation, events have proven to be determinants of water inputs in the American basins. The importance of ENSO events has led to a great deal of research by multiple organizations, which have produced multiple models aimed at projecting ENSO events in the short term. HI's research has led to the selection of the forecast for the ENSO event by Columbia University's International Research Institute for Climate and Society, IRI. The reason is simple: Hy does not have the economic capacity to implement its own model that would improve the Erie projections. Two types of models are used for ENSO prediction. Physic or dynamic, it is based on the physical explanation of the dynamics of the process, and statistical, based on empirical evidence of the process adjusted by probabilistic models. The Erie publishes the results of two projection methodologies for the ENSO index, which are described below. Subjective, based on a consensus between CPC, Climate Prediction Center, and Erie analysts. Objective, based on a mathematical model that determines the weighting factors of each of the available models, based on the results obtained in the past period, using a Bayesian combination of models. The graphs present the predictions for the two types of models. Dynamic and statistical. The graphs present the predictions for the two types of models. Dynamic and statistical. The graph presents the Bayesian combination of all models. Another model available is the North American Multimodal Ensemble. Case: rainfall runoff forecast models. Rainfall runoff models are based on conceptualizations of the hydrologic system that simulate the physical process that occurs in the basin, and converts precipitation into flow at the outlet of the basin. Among the most well-known models are the NWSRFS, U.S. National Weather Service River Prediction System. The high cost of implementing this type of model, which requires a large amount of physical data, is one of its main characteristics. These models divide the basin into sub-basins with homogeneous characteristics, and impose water propagation equations on them. The process of implementing the models involves a process of calibration of the physical parameters that characterize the sub-basins, which is generally carried out from a historical sample of precipitation and flow series with high precision, i.e., time level, or lower, for small basins and daily level for large basins. Hydrologic modeling. The research questions NWSRFS is currently pursuing are: how can we provide improved estimations of basin initial conditions, like soil moisture, snowpack, at the start of a forecast period, and how do we characterize hydrologic model uncertainties? The first question is considered under the topic of data assimilation, and the second question is addressed through the multi-model super-ensemble techniques in hydrology. Data assimilation. NWSRFS has implemented the ensemble KALMAN filter, INS-KF, in the SNO 17 model. SNO data assimilation using the extended KALMAN filter, EKF, is an elegant solution to the challenges posed by the EKF. Multi-model super-ensemble. NWSRFS multi-model super-ensemble technique mixes and matches various methods for modeling hydrologic processes to allow the construction of multiple models, all with different structure. We are using the USGS modular modeling system as an integrating framework. Case: short-term streamflow forecast. Using the theory of the unit hydrograph, in 1978, Velasquez used a multi-state Kalman filter for streamflow prediction in Venezuela's Caroni River Basin, using a KF parameter. The parameters are identified by the instantaneous unit hydrograph values. This is based on the function of a system's response reflects the way its internal structure works. Structural changes cause changes in the response function. One of the limitations in the modeling of uncertain dynamic systems is that related to the hypothesis that the response function is known a priori, and structural changes of the system cannot be easily modeled. A KF parameter is equivalent to a dual Kalman filter but ignores the physical filter. The dynamic parameter equation states that the value of a parameter at t is equal to the value at t plus the gradient over the period t1, and the value of the gradients is constant. The observation equation establishes the relationship between the unit hydrograph and precipitation measurements at various points in the basin. In this case, rainfall is assumed as a deterministic value, the same as in a linear regression process. The dynamic parameter equation states that the value of a parameter at t is equal to the value at t plus the gradient over the period t1, and the value of the gradients is constant. The observation equation establishes the relationship between the unit hydrograph and precipitation measurements at various points in the basin. In this case, rainfall is assumed as a deterministic value, the same as in a linear regression process. At steady state, the parameters that define the dynamics of the system do not vary. In the structural transitory state, the dynamics of the system are changing, translating the impact into changes in the parameter, and in the transient stochastic state, the system is affected by shocks due to its intrinsic probabilistic nature, which are not always explained by system dynamics, and are not due to structural changes, reflecting their effect on measurement errors. The proposed characterization considers that the entropy of a dynamical system is not independent of the state in which it is, and that it cannot be characterized by values of state variables, since this entropy can be generated exogenously, and reflected in the change of the variance-covariance matrices that depend on the state in which the system is. The table shows qualitative characteristics of these matrices. The application implemented in 1978 has the following features. Two basins, San Pedro and Aricuna, were modeled. San Pedro's model relates the flow in San Pedro to the upstream flows in Aricuna and La Paragua. Aricuna's model was based on precipitation measurements at 4 stations: Aricuna, Huancan, Cavanayan, and Uraman. The table presents the statistics of the World Meteorological Organization, WMO, for the implemented models. The quality of the predictions made with the KF can be observed, and the substantial improvement of MSKF with respect to the KF standard model. The MSKF model was delivered to Edelca, Electrificadora del Caroni. High/Climate is a forecast model that results of the use of the state estimation methodology to implement machine learning algorithms to understand the behavior of a hydroclimate system, using advanced algorithms based on the fundamental concepts that support the so-called KALMAN filter. The multiple-state KALMAN filter and the dual KALMAN filter are integrated to model the state of the watershed, estimating online the state variables and the parameter of the model. MSKF makes it possible to handle unexpected changes in system state at the level of the entire basin, as the process of climate change is occurring. The learning process associate to high climate is a deep learning process, since it assumes the process of identification of parameters as part of the dynamics of the system, without preset a response function as stationary and certain. The dynamics of the DMSKF allows to re-estimate the system response function considering the information contained in the data more recent. It may include the dynamic selection of the structure of the differential equations that explain the hydroclimatic process. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.